My talk today is on efficient importance sampling via optimal control for stochastic regression networks. And this is a joint work with Shihab Ben Hamouda, Nadia Ben Rachid, and Raul Tampone. And a few weeks ago, we have submitted a manuscript of this to Statistics and Computing. But there's already an archive preprint version online. So if you're interested, you are very welcome to have a look at our archive. Okay, before starting, I just want to drop the central names and the aim. And this is to introduce a novel connection between importance sampling and stochastic optimal control for stochastic regression network. And they are a special kind of pure jump processes. And based on this connection, we want to design a Monte Carlo estimator for our quantity of interest, which is the expected value of some observable G of the stochastic regression network at final time. Okay. Having this aim in mind, I will first introduce the general problem setting. Therefore, I will introduce stochastic regression networks, show you how to sample them. Then I will talk about the Monte Carlo estimator and about importance sampling. And then having these tools in my main part, I will talk about the connection between importance sampling and stochastic optimal control. And based on this, I will show you two different approaches. One suitable for lower dimensional stochastic regression networks, and the second one suitable for higher dimensional stochastic regression networks. And at the end, before ending, I will give you a short conclusion and an outlook. Okay, let's start with stochastic regression networks. Stochastic regression networks were originally introduced to model chemical reactions. But whenever we have a small number of molecules, the older deterministic approaches become insufficient because then the dynamics are dominated by stochastic effects. And stochastic regression network model the stochastic regs by Poisson processes or Poisson random variables. There are various applications for stochastic regression networks. For example, they can be used to model biochemical reactions, but also to model epidemic processes and to model the transcription and translation in genomics and virus kinetics. A stochastic regression network is a continuous time Markov chain, and we can describe the dynamics by the Kurtz random time change representation, which is given here in the gray box. And therefore, we basically just stack the number of molecules in a vector, which is called x, which is time dependent, such that the ith entry of this vector x is the number of molecules of the ith species. And in order to derive the molecule counts at time t, we start with the initial state vector, and then we just count how often each reaction takes place up to time t. This is then this variable rj here. And well, after having this count of the reaction, we then change the state vector accordingly by multiplying this times the state change vector, which gives the state change for one occurrence of a reaction j. Okay, the question is how to model this reaction counter rj. And this can be done with the help of unit rate Poisson processes. And they are independent for the j reactions we have. The parameter of this process is given by an integral over time over the so-called propensity function, aj. And the propensity function is a function of the state vector, which maps to a non-negative value. And whenever the propensity function is high, this means that a reaction channel fires frequently. A low propensity means that the reaction channel is less reactive, and a zero propensity means that there's no reaction in this reaction channel. Okay. Having the definition of a stochastic regression network, we can now state the general problem. And therefore, we assume to have a final time t and a stochastic regression network, well, going from 0 to final time t. Further, we have an observable, which we call g, and we have a prescribed error tolerance tau. And the aim is now to find an estimator m script of our quantity of interest, such that the probability that the error is smaller than the tolerance tau is larger than 95%. Or in simpler words, we want to find an estimator which fits our error bound in the sense of a 95% confidence interval. And of course, this estimator should be derived with minimal computational work. As observable, we can consider various functions, but in our work, we have considered two special functions. The first one is we map to the ith component of X. This is then an estimator for the average number of molecules of type I at final time. And the second observable is we take a subset of the state space, which we call B. And then the observable is given by an indicator function. And this is then an estimator for the probability that the stochastic reaction network at final time has a value out of B. The second observable can be especially used for rare event applications. So whenever this probability is very small, we talk about rare events. And we will later see that especially this setting is very challenging for Monte Carlo estimators. And this is actually the setting we are targeting with our new method. Okay, in order to derive an estimator for a stochastic reaction network, we need to have a way to sample it. And this is usually done pathwise. And we have two options. We can either use a pathwise exact scheme or a pathwise approximate scheme. In the exact scheme, we model the exact stochastic distribution of the process. Therefore, we can use various algorithms, for example, the stochastic simulations algorithm by Giles, or the modified next reaction method by Anderson. But the drawback of this is usually if we have one-off direction channel which fires frequently, this is computationally very expensive. On the other hand, we can use the approximate scheme, and therefore we fix some discrete time grid and only simulate for the discrete time steps. This is computationally faster, but might introduce a bias term. And actually in the example I've chosen here, so this is the same process for well, a set of, I guess, 100 sample paths. Both we can see that on the right-hand side where I have used a very rough grid, that we have some bias, for example, here in the peak, which goes up to 200, where the original one only goes up to 60. Okay, but if we choose the grid small enough, then the bias term can be controlled. In our work, we have focused on one approximate scheme, which is the tau-leap approximate scheme. The tau-leap scheme is basically just a stochastic version of an forward Euler scheme. And therefore, we assume that the propensity is constant on small time intervals. In our work, we have assumed to have a uniform time grid. So the step size is always delta t. And then we can transfer the Kurt's random time chains presentation to the so-called tau-leap scheme, given here in the gray box. And therefore, in each time step, we take the current value and we update this times the sum over all reactions over Poisson random variables, where the parameter is given by the propensity function of the current value times delta t. So the main difference to the Kurt's random time chain presentation is that we don't have Poisson processes, but just Poisson random variables here. And second, the parameter is not given by an integral over time, but just by the propensity of the current time step times delta t. This comes from assuming a constant propensity on each group step. The computational cost of this tau-leap scheme is of order delta t to power -1. And maybe an additional small remark, since we are assuming to have the setting of chemical reactions where we physically can't have negative molecule counts, therefore we project the value in each step to 0. This is why we have here the maximum term in the tau-leap scheme. Okay, having a way to sample a stochastic reaction network, we can now build the Monte Carlo estimator. And therefore, we sample m independent tau-leap path, denoted by x hat. And then the Monte Carlo estimator is the average of g of x hat at final time. This Monte Carlo estimator has two sources of error. The first one is the bias term, and the second one is the statistical error. The bias comes from using an approximate scheme instead of simulating the exact path. And we can show that this bias is of order delta t in the tau leap setting. And the statistical error, well, comes from the random samples and can be shown to be approximately given by C alpha times the square root of the variance of g of x divided by m, where C alpha is here from the quantiles of the standard normal distribution. The total computational work to reach an error tolerance of tau can be shown for this Monte Carlo tau leap estimator to be of order tau to power -3. A short remark on the statistical error. We can already see here that the statistical error scales with the square root of the variance of g of x. This means if we have a high variance in g of x, this becomes problematic because then the statistical error increases and we need more samples, which makes it computationally more expensive. I want to show you say this Monte Carlo estimator is especially for the setting of rare events expensive, and therefore I have here a small toy example where the aim is to estimate the probability that some random variable x is larger than some threshold gamma. And well, if we assume that this threshold gamma is large enough, then this value q, this probability becomes a rare event. We can derive a Monte Carlo estimator for this just by sampling m independent realizations of x, and then applying a Monte Carlo to an indicator function. One can also show that the variance of g of x, which is the variance of the indicator function, is equal to q minus q squared. And from this, we can then derive the statistical error, or in this setting, we consider the relative statistical error because we are in the rare event setting. And the relative error is approximately given by C alpha times the square root of 1 over q times m. And here in the denominator, there's the problematic because if q is a rare event, q is very small, and therefore this statistical error is very large. In numbers, this means if q is a value of 10 to the power -8, and if we're interested in estimating with a precision of 5%, so having a relative tolerance of 5%, then we would need more than 10 to the power 11 samples, which obviously is quite expensive. And therefore, especially for the setting of rare events, we need a way to make the Monte Carlo estimator more efficient. And one possibility to do this is importance sampling. Importance sampling is a special kind of variance reduction. So we aim to reduce the variance of g of x to reduce the statistical error. In importance sampling, we assume to have an auxiliary random variable z with some density rho hat. Then we have some mild conditions, but we can then reformulate our quantity of interest, which is the expected value of g of y, by expressing it as an integral, and then basically just adding a multiplication of 1. So we have now here a term of the original density divided by the auxiliary density times the auxiliary density. And this is then the same as the expected value of L of z times g of z, where L is the so-called likelihood factor, so the original density divided by the auxiliary density. So this means we have a form from the random, and on the right hand we have value with respect to z with the density rho hat. And this means if we choose z wisely, we can reduce the variance with having the same estimator. And looking at the flow chart at the bottom of the slide, reduced variance means we have need a smaller number of sample counts, and therefore we have a lower computational cost. The variance as much as possible. And this is actually the setting which we are considering in our approach for the setting of stochastic reaction networks. And we not only want to find a good auxiliary random variable, but we want to find the random variable or the random measure which reduces the variance as much as possible in the setting of stochastic regression networks. Okay, of course, it's not possible to consider all possible auxiliary densities, but we need to restrict ourselves to some kind of a parameterized class of important sampling measures. And this parameterized class of measures is based on the Taulib scheme. So here's a short recap. I've given the Taulib equation again, and you remember the randomness comes from Poisson random variables with parameter which is equal to the propensity times delta t. And the idea is now to keep the Poisson random variables, but to change the parameter of this Poisson random variables. And therefore, we introduce a set of parameters delta, and the important sampling random variables are sampled from a Poisson random variable with parameter delta times delta t. And this important sampling parameters, or this control parameters, are chosen for each time step n, for each reaction channel j, and for each state x separately. So this is basically a tensor of important sampling parameters. In order to fulfill the condition for important sampling, we need to choose this control parameters to be 0 whenever the propensity is 0, and otherwise we allow any positive value. The question is now how to choose these important sampling parameters to reduce the variance as much as possible. And therefore, we use the tools of stochastic optimal control. So in this setting, reducing the variance is the same as reducing the second moment. Therefore, we first define the second moment. And we define the second moment for a set of important sampling parameters delta. And we define it starting at time n in state x. So this is why we have an additional index nx here. And then the second moment is given by the expected value of the observable squared of the important sampling path at final time times the likelihood factor squared. In this setting, the likelihood factor can be easily derived because we have Poisson random variables as auxiliary random variable and as original variable. And we can derive the likelihood factor for each of the time steps. And then just by taking the product over all time steps, we get the total likelihood factor. Based on the second moment, we can also define the value function. This value function is again defined starting at time n in state x, and is the infimum over the important sampling parameters of the second moment, given here in blue. Usually in stochastic optimal control, one can now find some dynamic programming relation or set of backward equation to find this value function for each time step and for each state. And actually in this setting, we were also able to find such a formulation, which is given on the slide. So we have here a set of backwards equation, since the value at final time at the bottom of the slide can be just derived by the definition of the value function, and is equal to the observable squared. And then we have an equation which allows us to derive the value function backward in time. So here on the left-hand side, we have the value function at time n, which relates to the value function at time n plus 1 on the right-hand side. And the right-hand side is a small minimization problem. So we have here the infimum over the important sampling parameters, but just of the current time step, of some exponential term and some sum where the parameters only depend on the value function at n plus 1. Okay, and in theory, we are done here. So we could use this theorem to derive the value function for each time step, and also by solving this minimization problem to derive the optimal important sampling parameters. And they could then be used in a forward run to sample the important sampling path. The problem is that this minimization problem here on the right-hand side is non-trivial, and that we also have here an infinite sum, because we are summing here over all possible increments. And they, of course, they are not finite. And therefore, we have applied to the theorem a truncation of the Taylor series and also a truncation of the infinite sum. And doing so, we result in a simpler formulation, which we now call U bar instead of U. And we still have that at final time, we have the observable squared. And then we still have a set of backward equation, but now we can solve this backward equation in a closed form. And we can also find the important sampling parameters related to the value function at time n+1. I should note this solution in the second box, this closed form solution, only applies if the value function at time n+1 is non-zero and if the propensity is non-zero. In the other cases, one needs some special numerical treatment, but I don't want to go in detail. But you can have a look in the paper if you're interested. But the case which is given here is basically the standard case, which usually applies. Okay. Okay, having this in hand, we can now derive, based on this derive different approaches. The first approach is just a straightforward implementation on what you have seen on the previous slide. So we just straightforward implement the dynamic programming. And by this, we get a tensor of optimal importance sampling parameters, which then in the second step can be used to simulate the importance sampling path. We will also see later that this is only suitable for lower dimensions. In higher dimensions, we get some problems, which I will discuss later. And for this higher dimensional scenario, we have derived a second approach, which we call the learning-based approach, which I will present in the second part of this talk. Okay, but first, let's stay with the direct implementation of the dynamic programming. As I said, we have a backward step where we derive the optimal importance sampling parameters as a tensor. And then we have a forward step where we use this importance sampling parameters to simulate the importance sampling path. So for each time step, we look in the tensor, which importance sampling parameter is optimal, plug it in, and then for the next time step, we look again in the tensor. The total computational cost is therefore also split into paths in a backward step and a forward step. And we can show that the backward step has a computational cost of delta t to power -1 times the number of reaction times the number of states to power d. And of course, we need here to find some upper bound for the states. And the forward step is then the number of paths we simulate, m times a cost which is the same cost as the cost of standard tau leap, with an only additional factor for deriving the likelihood factor. A short remark on this backward cost. We see here that we have the term s to power d. This means that this backward cost scales exponentially with the dimension of the stochastic reaction network d. And this, for large dimensions d, becomes problematic and quite expensive. And that's why we call this the curse of dimensionality. And that's also why we later on need a different approach for higher dimensional stochastic reaction networks. But for small dimensions, especially for dimension 1, we have get very good results for this estimator. We can even show numerically that we have a decaying variance of order delta t. And this decaying variance of order delta t means that we also reduce the number of required paths to derive a prescribed error tolerance of tau. So this means our novel approach, the importance sampling approach, only requires tau to power -1 sample path, whereas the standard tau leap estimator requires tau to power -2 path. So we reduce this by a whole order. And this reduced number of paths also propagates to the total computational complexity, such that we can reach a computational complexity of tau to power -2. To demonstrate these rates, I have two examples, both 1D examples. So I have first the pure decay stochastic reaction network. This is a reaction network with just one reaction. And here we consider the observable, which is the identity. And second, I have a birth and death stochastic reaction network. Here there are also 100 paths of the stochastic reaction network plotted over time. We have here two reactions, one birth reaction and one decay reaction. And here we consider array event observable, and we are interested in the probability that a time is larger than 40. And well, looking at this plot, you can already see in 100 path, the highest value is 60. So a value higher than 40 is this plot array event. Okay, let's start with the decay stochastic reaction network. In this plots, we have always in red as reference the results for standard Tau-Leap Monte Carlo estimator, and in blue the results for the novel importance sampling estimator. And the first two plots also have confidence intervals, which are derived from bootstrapping. But they are rather small in this first plot. Well, for quantity, we can check that the sample mean is the same for our novel approach as for the standard approach. So the estimator is the same. And looking at the variance, red, and the variance of our novel approach is decaying with order delta t in blue. And if we're now interested in the number of samples required to reach a prescribed error tolerance of tau, we can here see in the third plot that for the novel approach, we need to pronounce 1 sample in the standard order of tau to power minus 2. And therefore, also the total computational will need tau to power minus 2. Time. Example is the the stochastic reaction network with 2 reactions. Here we have a array event of order 10 to power minus 4, which can be seen here in the mean plot. And again, we have a decaying variance of order delta t, at least in an asymptotic regime for small delta t. This variance here is not, here's not the variance plotted, but the squared coefficient of variation, which is a scaled version of the variance suitable for array events. And we are also not considering in the second in the third and fourth plot the leptons. And we can see here that the number of required samples for our novel approach is of order tau to power minus 1 and tau to power minus 2 for the standard approach. And to demonstrate how much of a reduction this is, we can look at the value 10 to power minus 3, so relative tolerance of 10 to power minus 3, where we can see that the standard approach would need approximately 10 to the power 11 samples, and the novel approach only needs 10, maybe 10 to 6, 10 to 5 samples. So we have here a reduction of required samples by a factor of almost 10 to the power 6. And that's also the reason why I was not able to do the total computational work for the standard approach. This is just too much samples, and we only have total computational work, which again reaches the Okay, after having this approach, we now want to talk about higher dimensional stochastic reaction networks. And we have seen that the straightforward implementation of the dynamic programming is problematic because the backwards of the step scales exponentially with the dimension d. And therefore, we need, well, a different approach for higher dimensional stochastic reaction networks. And that's why we have developed the learning-based approach. And here we model the ansatz function, the value function u bar, by a parameterized ansatz function. And this parameter is called beta. It's important to note that this parameter set beta is way smaller than the set of importance sampling parameters. So beta is in our simulations just d plus 1 dimensional. And we try to fit this parameter's ansatz function to the value function by a stochastic optimization algorithm to find the beta parameter. Having such an ansatz, we can then use the connector between the value function and parameters, which we have from the dynamic programming theorem. And this means that we don't need a dedicated backward step, but we can, in the forward step, on the go, derive the important sampling parameters by plugging in derivation. Therefore, this approach does not suffer from the curse of dimensionality. So we just important sampling parameters. Okay, to go in more detail, you remember the value function is given at the infimum over the important sampling parameters of the second moment. So this is given here again. And we now assume to use an ansatz function, which we call u hat, to model this value function. And this ansatz function is given with the parameter beta. And then in the forward step, we just use the relation known from the dynamic programming theorem to derive the important sampling parameter based on this ansatz function. This is this equation here. How can such an ansatz function look like? If we consider the array event setting, our simulations have shown good results for a sigmoid-shaped ansatz function. And therefore, we have considered a sigmoid with two sets of parameters. Like we have here the blue parameters and the red parameters. And actually, if we choose the sigmoid like this, you can see that plugging in the final time value, only the red parameters are relevant. And since we know that the value function at final time is given by g squared, this allows us to fit the sigmoid at final time to this value of g squared by choosing the parameter b0 and beta 0 accordingly. And the parameter beta x and beta n are then responsible for the shape, the steepness, and the position of the slope for all other time steps. This means the only parameter we need to somehow find in order to fit the value function are the parameters beta x and beta n, the blue parameters. And these parameters are in this setting, have a dimension of d+1. Okay, how to find the parameter beta? You remember the value function is the minimal second moment. This means we again find the parameter beta by minimizing the second moment. And in this case, we are minimizing the second moment of the important sampling path based on beta. This is x bar with the additional parameter beta. And well, this are the important sampling path which are derived by using the relation between the important sampling parameters and the value function u hat. Should note, for arbitrary beta, these are not necessarily the optimal important sampling parameters. These are just some important sampling parameters. But for when we find a way to minimize this, these parameters become more optimal over time. How to solve this minimization problem, which is given here? We did this with the stochastic optimization algorithm. You could, for example, think about gradient descent, or we used in our work the Adam optimizer. But in order to apply such a stochastic optimization, we need a way to find the gradient of the second moment. This derivation is quite technical, but the partial derivatives with respect to beta L are given on this slide, and they are again given as an expected value of a term which is dependent on the important sampling Tolly path based on beta. And well, having this formulation, we can then approximate the gradient by using a small Monte Carlo estimator for the second expected value. And then, well, having the gradient, we can just apply gradient descent or Adam to step-by-step optimize the parameter beta. To demonstrate this, I have three examples. The first example is a pure decay stochastic reaction network again, now with the array event observable. Then I have a four-dimensional example, which are the Michaelis-Menten enzyme kinetics. And the last example is a six-dimensional stochastic reaction network, which is called enzymatic Futel cycle. And for all three of them, we use array event observable with the shape ansatz function you have seen before. Okay, in this plots, I know always fix the step size delta t, so we don't vary the step size, and the x-axis are giving the values for the optimizer steps, and here we use, for example, 100 optimizer steps. In dashed red, we have always a reference line which is derived from the standard Monte Carlo Tau-Leap approach with a high number of sample paths, and this is constant for all optimizer steps, because the simulation is just done once and then fixed for all steps. And the black line is then how the novel approach varies with the number of optimizer steps. So this first example is a ray event of order 10 to the power minus 3. And we can see that the squared coefficient of variation, so the scaled variance, starts with around the same value as the standard Tau-Leap variance. But after a little more than 10 steps, we reduce the variance by a factor of 100. And this is achieved with only having a parameterized ansatz function with the 2 parameters in the setting. So we only have beta x and beta n. Another advantage of this approach is that we reduce the kurtosis. The kurtosis is connected to the robustness of the variance estimator. And we can here see that we reduce the kurtosis compared to the standard Tau-Leap approach. Second, we have the 4-dimensional example. We have no array event of order 10 to the power minus 5. And here we can see that the initial value for beta was already quite a good guess. So we have already, with the first step, quite a high variance reduction. But after some more steps, we slightly reduce it further, such that we have a variance reduction of a factor 10 to the power 3. And again, we are also reducing the kurtosis. Okay, and the last example, the 6-dimensional example, is also the most rare example. Here we have a probability of 10 to the power minus 6. And well, looking at the mean, we can see how here the standard Monte Carlo Tau-Leap estimator is failing. Because even for a high number of samples, we have a mean which is, well, not the same as the importance sampling mean, but actually we can trust the mean from importance sampling more, since the variance is lower for this estimator. Here we reduce the variance by a factor of 50 after 43 steps. And again, we have also reduced kurtosis here. Okay, and well, with this, I want to give a short conclusion. We have established a novel connection between importance sampling and stochastic optimal control for the setting of stochastic reaction network. And this is a connection which has not been in literature before for the setting. And based on this connection, we have developed 2 approaches. The first one is a direct implementation of the dynamic programming theorem. We achieve here a variance reduction of order delta t for 1-dimensional examples. And with this, we have a total computational cost, which is of order tau to the power minus 1. The drawback of this method is that this becomes computationally expensive because we suffer the so-called curse of dimensionality. And to overcome this, we have a second approach, the learning-based approach, where we overcome this problem by using a set of ansatz functions for the value function. And then we still have a decent variance reduction compared to standard Monte Carlo Tau-Leap. And in addition, we also have a robust estimator for the variance because we are also reducing the kurtosis. A short outlook on what could be next. Considering the first approach, where we have a decent variance reduction of order delta t, one can think of applying this also to higher dimensional stochastic reaction network by combining this approach with a dimension reduction technique. So means taking the higher dimensional stochastic reaction network, somehow reducing the dimension, and then using this first approach. Alternatively, one could also think about the second approach, and instead of just using a crude Monte Carlo importance sampling estimator, one can think about combining this with some multi-layer technique to make it more efficient. And with this, I want to thank you for your attention. and I'm looking forward to